Nuclear reactions. We need to finish up nuclear reactions depending on what period you're in. The very first little bit, maybe review or not. But we need to finish up decay and talk about half-life briefly, and then mention transmutation, fission, and fusion for you. So the first thing that we need to understand about decay, and we went over the types of decay, alpha, beta, gamma, etc. in class, is that decay is a first-order process, which goes back to our kinetics ideas. If you remember, 0 and first and second order back when we did kinetics. But decay, radioactive decay, is a first-order process. So when we look at a graph of the amount of the radioactive substance that remains over time, it gradually decomposes in an exponential decay kind of a way. Reaction from back when we did kinetics, or I'm sorry, an equation from back when we did kinetics is natural log of x over x naught equals negative kt. And in this case, what this is referring to is this is the initial concentration at the beginning. This is the concentration that remains at time t. K is the rate law constant, not KEQ, you guys, back to rate law constant, and T is time. So if I rearrange it, because that's how I'm going to use it here a little bit, I'm going to get rid of the negative and just make it KT. So now initial concentration goes on the top. What we're concerned with here is half-life. Because with radioactive substances, they last a really, really long time, so we're interested in a half-life, not how long they last. So at half-life, if I have half of it, this number here would be 100%, and the number on the bottom would be half. So I could just do the natural, ooh, sorry, don't want to write in a highlighter. Natural log of, say, 1 over a half is equal to KT, and I can rearrange that. This is, of course, the natural log of 2. And if I want to rearrange it to find the rate law constant, it becomes the natural log of 2 over t. Natural log of 2 is 0.693 over t is equal to k. And we can call that t 1/2. So this is a way to find rate law constant if you know the half-life, or find the half-life if you know the rate law constant, either way. So the half-lives range from anywhere from really, really big. An example might be, let me scroll down a little bit more. Neodymium 144, the half-life of that is 5 times 10 to the 15th years. Think about how big that is, you guys. Humongous. To polonium-214, half-life of polonium-214, 2 times 10 to the minus 4 seconds. So some of them last a really, really long time, and some not so much. I'm going to give you another formula in addition to one I just showed you with kinetics, but kind of a simple one that some of you may have learned in Chem Honors, is the formula of 1/2 to the n is equal to the fraction of the original sample that remains after n half-lives have passed. So what I'm going to do is I'm going to just do an example, and I'm going to show you two different ways to calculate that example. And so we're going to look at carbon-14 decay, which is how they date fossils and things. And carbon-14 decays, now if you look at that, it's got too high of a neutron to proton ratio. So if you, based on what we talked about in class, it would not be unusual for us to consider that it's going to decay by beta emission, which is going to make it turn into nitrogen-14, which is stable because it's got a 1-to-1 neutron to proton ratio. So here's the question. How old is a fossil that contains only 16% of carbon-14 compared to a living thing? Now there's a limit to carbon-14 dating because eventually the equipment we have can only determine a certain level of carbon-14. When that level drops below, you know, say 1% or so, we just simply don't have the equipment to date it anymore, so there's actually a limit. All right, first way I'm going to show you is using our kinetics equation. And so in order to use that, we do need to know that the half-life of carbon-14 is 5,730 years. That's going to be an important piece of information. So, method 1. If I use method 1, I could actually solve for the rate law constant. And so I can use the equation k is equal to 0.693 divided by the half-life. So 0.693 divided by 5,730 years is my k. And so if I plug that then into my natural log of x naught over x equals kt, if it's 16%, then my original will call 100 and my 1 at time t, eek, will call 16. So natural log of 100 over 16 is equal to, here's my k value, I'm just going to go ahead and plug it in, 0.693 over 5,730 years times t. And if you solve for t, you get 15,200 years. So that's one way to get an answer to the question. Another way to answer that same question, method 2, is using the other equation I gave you. And that is where you take 1/2 to the nth power is equal to the fraction that remains. Well, the fraction that remains is 0.16. Just taking my percentage into a decimal. All right, if you're going to use that, we've got to take the log of both sides. So n log of 1/2 is equal to the log of 0.16. And you can go ahead and solve for n, and n is 2.64. But that is related to the number of half-lives. So I'll take that, and I know that there's 5,730 years per half-life. And so I get 15,100 years. So I know it's off by a little bit, and that's rounding from the different methods. But essentially, in a problem like this, you could solve it more than one way. Which way should you choose? Depends on the problem. Some ways it's going to be easier to just do this. Some ways you're going to need the rate law constant. So it just kind of depends. All right, the last things then, I'm just going to briefly mention the other 3 types of nuclear reactions. So number 2, first one was decay, of course. Number 2 is transmutation and bombardment. And this is basically what is, like I mentioned, it's artificially done. And so this is what's done in particle accelerators. This is really how they make new elements. And what you need to understand is that these are how they make all the trans-uranium elements. What do I mean by that? Well, it turns out that uranium is the last naturally occurring element at all. And uranium is atomic number 92. So that means that anything with an atomic number greater than 92 is man-made. And if you look at a periodic table, that's quite a few elements that are man-made, like americium, californium, things like that, plutonium. And it doesn't mean they don't have uses. Plutonium is used in weapons, and it's a byproduct of the fission reaction, but is done by neutrons bombarding something. Americium is found in smoke detectors. So they do have uses. It's just they do not exist naturally. So an example might be by taking an alpha particle and bombarding it into, in this case, say boron 10. They accelerate these at a really high rate of speed. Now think about it. They have to hit just right in order to actually fuse into something larger. So you've got to get them accelerated very, very quickly. Have good aim. think about that. Okay, 13 and 7, nitrogen. And so we basically put these two smaller things together and we get something larger. And this also gives off a neutron, which is not unusual. And of course, this particular one is giving a radioactive product. Do you know why? Okay, so that is transmutation. Number 3, fission. This is, as I mentioned, what is in our nuclear reactors. It's what's in the atomic bomb. And essentially what happens with fission is there are some elements that, you know, they have an unstable nucleus, but they just don't tend to break apart on their own. But if they get hit, say by a neutron is hitting a uranium, they will just spontaneously break apart into smaller pieces. Like in this example, krypton and barium. So this one large one literally split into 2 other ones. And there's often neutrons given off as well. And energy. And this was actually discovered by Lise Meitner and Otto Hahn. And they were trying to just simply make bigger elements. So they was trying to shoot neutrons into uranium to make bigger elements, but they never made a bigger element. Instead, they kept getting smaller elements out of it. And a lot of energy, because what happens is there's mass lost. When these come together and form this, mass is lost, and according to Einstein, equals mc squared. The mass that's lost when related to the speed of light squared counts for some energy, and so you get energy out of it, and that energy is used to heat water in a nuclear reactor. Let me find a quick picture of fission. That's what I want. So if you look at this picture here, this is just a little pictorial. Here's your neutron coming in and hitting uranium. It's splitting. But what you're not seeing are these little things. These are neutrons that have been also given off, and they can hit more uranium and split that, and hit more uranium and split it. And eventually, if you have enough uranium that reaction keeps going, you have a chain reaction. But in order to have enough of that to keep going, what you need is what's called a critical mass of uranium. And a critical mass of uranium is enough reaction to start a chain reaction. And that's the premise of the atomic bomb. It actually has a critical mass of uranium that they split into 2 pieces. And then those 2 pieces on impact actually come together and form a critical mass, and they usually have something that's giving off neutrons. Boron often gives off neutrons, and it causes a chain reaction. And each time here, this gives off energy, these give off energy, and suddenly you have so much energy that's being given off that it explodes like a bomb, and that's the premise of the atomic bomb. In a nuclear power plant, they do not have a critical mass worth, so energy is given off, but not enough to explode like an atomic bomb. If I look, let's see if I find it here. So if you look at this picture of a nuclear power plant, what they have inside of, this is the nuclear reactor, and these black things are actually the reactive uranium. And they have these control rods which they lower or raise up in order to allow this reaction to progress. It's a chain reaction, but not an uncontrolled chain reaction. And so that ends up actually giving off heat that is transferred to this water, which is the moderator. That heat is transferred to some water, which turns into steam, which runs a turbine. There's another tertiary water supply that cools the water back down into liquid water, and the process continues. And they keep raising and lowering these control rods in order to allow more heat or less heat. And this here, this is the containment vessel I was mentioning in class. Okay, back to where we were. So that is fission, and we get a lot of energy out of it. The thing we have to know about these guys is this is the radioactive waste, because they have the wrong neutron to proton ratio. And so when we talk about nuclear waste, this is what we're talking about, are these byproducts here. All right, last one, and I'll just mention it very briefly. Fusion. That's what we find on the sun in a hydrogen bomb. Fusion takes two very small particles, like this is deuterium, which is heavy hydrogen. It's got a proton and a neutron. When you take those and you slam them together at a very high rate of speed, which takes a very, very, very high temperature to get them going fast enough, even when they hit the walls of a container, they slow down too much and they won't fuse. So that's why they often use magnets, so that they don't hit the walls of a container. It will actually fuse into, in this case, helium. This is not an alpha particle. There's no radioactivity here. It's actually a helium atom. But in doing so, mass is lost. And so as a result, you end up with a lot of energy. And that's, again, related to the fact that if mass is lost, you end up getting energy out of it. We don't use this for power because we don't have good ways to really continually get this high rate of speed for them to fuse, and the amount of energy you get is so much more than what you get with fission. We don't have a good way to control it. But it is what's used in the hydrogen bomb, and the way that they get the high rate of speed for the fusion reaction in a hydrogen bomb is they actually use a fission reaction to fuel the fusion reaction, and then so much energy is given off in the fusion reaction, it is incredibly destructive as a result of that. So that finishes up our 4 types of reactions, and then I will see you in class tomorrow.